So we'll discuss about the spanning tree in this graph. Suppose there is a graph like this, and let's say this graph is a complete graph. The complete graph means every vertex is connected with every other vertex. In the complete graph, the degree of any vertex is v minus 1, means total number of vertices minus 1, because from each vertex 3 edges will be emerging. For this particular graph, v minus 1 edges will be emerging, and the total number of edges in this graph will be v into v minus 1 divided by 2. Here in this case it will be 4 into 3 divided by 2, means 6 edges. You can count that the number of edges here is 6. So if we form a tree from this graph which has the same number of vertices but less number of edges, and the resultant tree or the resultant graph is a connected graph. So this is a connected graph. From this I have prepared this. This is also a connected graph. By some means I can reach to every vertex. Now in this graph, if you see, there is no cycle, so we can say that this is a acyclic graph, and this is a acyclic graph, means there is no cycle, and this is a connected graph. So this is a connected and acyclic graph, and it has the same number of vertices of the original graph. So this actually is the spanning tree of this graph. So what is a spanning tree? Spanning tree, let's say this spanning tree graph is represented with T, and this graph is represented as G. So this G, let's say, is represented with V and E. Then T will be represented as V. Obviously it will have the same number of vertices as that of the original graph, but the edges set will be different. Out of the 6 edges we have selected 3 edges. So we will say that this E dash is actually the subset of E. So as a definition we can say that the spanning tree T equals to VE dash of a graph G equals to VE is a connected acyclic graph with E dash subset of E. Once again, spanning tree T equals to VE dash of a graph G equals to VE is a connected acyclic graph with E dash subset of E. Fine. Mathematically, if you want to find out that how many spanning trees will you find will be there for a particular graph. For example, for this graph only, there are several spanning tree possible. This is one of the spanning trees possible. This another spanning tree will be this one. Another spanning tree will be this one. Fine. Another spanning tree will be this one. So there's several spanning tree possible for the same graph. So if you want to find out how many spanning tree will be there in totality, then the formula for that is n raised to the power n minus 2, where n is the total number of vertices. For this graph it will be 4 raised to the power 4 minus 2, it means 4 square, it means 16. So the total number of spanning trees possible for this graph will be 16. Now out of this graph, let us suppose that in this graph the distances are also mentioned. For example, 10, 7, 6, 3 and 8. Let's say this is 11. So the distances on each of the vertex is also mentioned. Each of the edges is also mentioned. And we want to find out a spanning tree in which the sum of the cost of each of the edge is minimum. Sum of the cost of each of the edge is minimum. Then we will say that this is a minimal spanning tree. So a minimal spanning tree, obviously it's a spanning tree If it will satisfy the property of the spanning tree, it will be a connected acyclic graph with the same number of vertices as that of the original graph. But the condition is that the spanning tree, in this is kind of the spanning tree, the total or the sum of the cost of the edges will be minimum. So if we have this graph, then this 3 and this 6, this is the minimum cost edge, this is the next minimum cost edge, 7 will be the next minimum cost edge, but by adding 7 it will be making a cycle. So in the spanning tree there has to be no cycle. So we'll discard this 7 and we'll take the next edge that is of cost 8. By this way all the vertices are connected. So this is the minimal spanning tree. So a minimal spanning tree will satisfy all the properties of the spanning tree. Alongside it will be designed such that the sum of the cost of the edges will be minimum.